Yeah, hi everybody to this new session of the Chilean probability seminar. So today's speaker is Lyuben Lichev from TU Vienna, and he'll talk about a great result, I think, which is about the mixing time and about the diameter of the giant component in the percolated hypercube. So please, Lyuben, go ahead.
Thank you very much, Dieter, and yes, thank you very much for inviting me to your seminar. It's a pleasure to talk to you about this work. So first of all, I'd like to underline that it's actually a joint work with my wonderful colleagues Michael Anastos from IST Austria, Sahar Diskin from ETH Zurich, and Maksim Zhukovskii from the University of Sheffield. So everything I'm going to say is based on work with these three wonderful guys. So first of all, probably all of you know what a hypercube is, but let me introduce it formally. So the d-dimensional hypercube is a graph whose vertices are the binary vectors of length d, and two edges connect two vectors which differ in exactly one coordinate. So here is a picture of the three-dimensional hypercube, for example. And it's not hard to convince ourselves that in general, QD is a deregular graph. So this means that every vertex is connected to the other vertices. It's bipartite, and it also has 2 to the d number of vertices. So what are we going to do with this graph? Well, we're going to percolate it. And as probably all of you know, so a p-percolation on a graph is a random process where we retain every edge with probability p independently for different edges. So we're going to look at random subgraphs of our cube, which looks something like this. So the p-percolated hypercube is one of the most standard models in random graphs, perhaps second only to the Elias-Renyi random graph, where we percolate a complete graph instead of a hypercube. And so our focus today will be on the sparse supercritical regime, meaning that our expected average degree will be more than 1, but it will still be some constant. And so for this model, there has been quite some work. So let me discuss probably two of the most standard references for it. In 1982, so Aitai and Semeredi have proved that in what I said to be the supercritical regime. So there are reasons for that. So there is actually a giant component there which contains constant proportion of the vertices. And 10 years later, Bolobashko, Hayakawa, and Luchak proved something more. So they showed that the second largest component is of order big O of D, which so D here is a logarithm of the number of vertices. And they actually proved something more. They proved that the percolated hypercube satisfies the so-called Erdős-Rényi phenomenon. So you can compute the expected number of vertices in the giant, and this proportion of vertices is actually the same as in the Erdős-Rényi random graph, and the proportion of vertices in components of size 1, 2, 3, 4, 5 is actually exactly the same as well as in Erdős-Rényi random graph. So there are actually many similarities with this most classical setting.
Lyuben, sorry, can I interrupt you for a second?
Yes,
Is it true that there's also discrete duality here in the same sense as in Erdős-Rényi graph, that in the subcritical case the largest component is the same basically as the second largest in the supercritical case?
indeed. Yes, indeed. This is part of the similarities with Erdős-Rényi graphs, yes.
Yeah, thank you.
Um, so today we're going to be interested in mixing time of certain random walks. And in order to introduce what this is, I have to tell you something about Markov chain. So let's have a very quick crash course on Markov chain. What is this? Well, these are a class of stochastic processes which are described by their state space S, their transition matrix P, and the initial distribution lambda, which is some probability distribution on the state space S. So in this talk, I'll be only interested in discrete time Markov chains on some finite state space. And what is important for these processes is that at every step, we are in some state of this space S, and what the next state will be is actually described by this transition matrix P, and it only depends on the current state. So we kind of lose our memory to what happened before that with our trajectory. We are only interested in our current state. And so why are Markov chains important? Well, they actually pop up in a number of practical and theoretical examples. Maybe some of the first examples, let's say at least combinatorial examples, are different types of randomized card shuffling algorithms. There are also many cases when we want to analyze some distribution on the vertices of a graph, say, and we can do this by a random walk. So there are different stochastic algorithms which are related to random walks and which use Markov chains. Maybe for people in statistical physics and in mathematical physics, the Markov chain by default is Glauber dynamics, where we have a graph and we have spins on the vertices of the graph, and these are consecutively updated. And of course, Markov chains in practice are used for a number of sampling algorithms, so in particular Monte Carlo algorithms. And the important, maybe the most important feature for Markov chains is the existence of a stationary distribution pi for, let's say, nice Markov chains. And this is a distribution which, so it gives certain weights to vertices, and these weights, roughly speaking, correspond to the frequency of the visits of a Markov chains to the particular states in the space after a sufficiently large number of steps. So we said what the stationary distribution is, and for these nice Markov chains, when the number of steps in the Markov chain is suitably large, we actually converge to this stationary distribution, but it's also important how fast we converge. So the mixing time is what actually characterizes, quantifies how fast we converge to the stationary distribution. So here by px dot, I denote the probability distribution given by the Markov chain started from x after t steps. Pi is our stationary distribution, and when we maximize this total variation distance over all possible states x, and we want this quantity to be at most 1/4, so the smallest t for which this happens is our mixing time. So why are mixing times important? Well, I can at least talk from combinatorial point of view. There are many sampling algorithms like Monte Carlo, as I said, but there are also cases where we can count using Markov chains which mix fast. So for example, there was a relatively recent work on counting independent sets in graphs and hypergraphs using a similar idea. So let's do a quick motivating example on mixing times. So I mentioned that some of the most classic examples of Markov chains are decks of cards that are shuffled in different ways. So if you take a deck of cards, then maybe one of the most natural things to do when you want to mix it is to cut it somewhere in the middle and then to intertwine the cards from the two parts that you obtain randomly. So what would the state space be here? The state space would be, of course, all possible arrangements of these cards, which are usually 52 in a usual deck. So the distribution, the stationary distribution towards which we will be aiming is the uniform distribution on the all possible permutations on these 52 cards. And Byron Diaconis in 92 proved that actually if we have a deck of n cards more generally, then the mixing time for this dynamics here is roughly 3/2 time binary logarithm of n, which for us means that, okay, if we actually do this rifle shuffle operation 7 times for a typical deck of cards, then we can be sure that we are relatively well mixed, so sufficiently well mixed for all practical purposes. So this is not the Markov chain that we'll be looking at. Our interest will be directed towards lazy random walks on our percolated graph. So what is this? The lazy random walk is the same thing as a simple random walk. So in particular, it chooses a random neighbor uniformly at random and goes there, but only with probability 1/2. So with probability 1/2, it can just decide to do nothing and stay in place. So why do we actually need this laziness? Well, simply because our hypercube is bipartite. So if we want to break periodicity of this random walk, which if it wasn't lazy, it would change from even states to odd states and vice versa at the next step. So this laziness actually means that the Markov chain is aperiodic. And since we are looking at the giant component, so our graph will also be connected, and connected graphs, so the lazy random walk on connected graphs actually has a very simple stationary distribution. And also the stationary distribution is tightly connected to the expansion properties of the graph, something that we're going to see in a little bit. For the moment, I'm going to say that these expansion properties actually concern what is the size of neighborhoods of connected sets of particular size k. So I give you all connected sets in your graph with k vertices, and then I ask you, well, how large are the neighborhoods of these sets? This will, in some extent, to some extent, give you information for the mixing time of the lazy random walk. But more about that in a bit. Let me first direct your attention to what is known in general for the lazy random walk on giant components of random graphs. And as I said, maybe the most standard and classic example in random graphs is the Erdős-Rényi graph. So the mixing time of the giant component here was considered by two independent papers by Beniamini, Kozma, and Vormaut, and by Fontoullakis and Reed. Don't pay attention to this difference of 6 years here. The papers are really independent and they went out in the same time. Both papers showed that actually the order of the mixing time of the lazy random walk on GNP in this sparse supercritical regime is of order log n squared. The situation for percolated d-dimensional boxes was studied by Beniamini and Mosel in 2003, and they managed to pinpoint the right order of the mixing time of the lazy random walk. This is n squared. So let me underline here that d is a fixed number, so the dimension is fixed, and the size of the box, so this n, is our asymptotic parameter. It is what tends to infinity. And in their paper, they ask, well, what if we do the opposite, actually? What if we fix n to be equal to, I don't know, 1, 2, and we make the dimension go to infinity? So essentially the situation with the high-dimensional hypercube. And this problem was considered by Erdekan and Krivelevich in 23. They showed that the percolated hypercube has mixing, so the mixing time of the giant component here in the sparse supercritical regime is polynomial in D. So polynomial in the dimension, again, this means logarithmic. So polylogarithmic in the number of vertices. One should always keep in mind that the number of vertices is 2 to the D here. And a year later, this was improved to D squared times some polylogarithm in D. So what's the hard part here? So I showed you So the first two results are exact up to constant, and the second two results are upper bounds. And I'd like to argue that actually the lower bounds are the easier part here, and they all come from sort of one-dimensional abstractions. So in the first case, and in the case of the hypercube, so both for GNP and the hypercube, these one-dimensional abstractions are long paths which start at a degree 1 vertex and only consist of degree 2 vertices. So in GNP, we have such called bare paths of length log n. And if you start in the end of such a path, so in the vertex of degree 1, in order to reach essentially a vertex of degree 3 in your graph, you have to cross a path of length log n. And the lazy random walk will do this in time which is roughly logarithmic in n. And for the percolated hypercube, we again have some paths which have length of order d and end with a leaf. So in order to be able to cross such bare paths, starting from the leaf vertex in the end, this will take us time d squared, roughly. So for the second point, the one-dimensional abstraction is a little bit different. So here one should project on one dimension, and then the intuition will be that if we do a random walk on the giant component of this percolated grid, then on what are we going to see on one of the dimensions? Well, probably something that resembles a random walk in one dimension. So this n squared is to be expected in this case as well, although the abstraction is a little bit different. And okay, so based on the first 2 points, and that these one-dimensional abstractions actually gave the right order. So Perez asked, well, is actually the same thing true for the high-dimensional hypercube? So is it true that the mixing time is of order d squared? And it turns out that it is of order d squared. So this is one of our main results, that with high probability, the mixing time of the lazy random walk on the giant component of our percolated hypercube in the supercritical regime is actually indeed of order d squared. So let me tell you maybe something about the approach that we're using. And the approach starts with an approach already used by Fontoullakis and Reed to describe to give an upper bound for the lazy random walk, so for the mixing time of the lazy random walk on GNP. So what did they say? Well, they said, let's bound T-mix. So we can actually bound T-mix using the conductances of sets. And so these conductances are actually proportional to some formula that I wrote here. So E of S comma V minus S, this is the number of edges that go from S to its complement in our graph. So E of S is the number of edges with 2 endpoints in S, and E of V minus S is the number of edges with 2 endpoints in the complement of S. So these conductances here, they are essentially proportional to the number of edges going out of our set. And what is their importance? Well, Fontoullakis and Reed actually show that T-mix is upper bounded by some sum of something that looks like the conductances, and these quantities here, that they are essentially minima over the conductances of sets which have some particular weight under the stationary distribution of the walk and are connected. So the intuitive statement that one should think about is that these sets S, if we forget about the pi, then we should think of sets which contain between 2 to the minus k minus 1 and 2 to the minus k proportion of all the vertices in the giant component. This is actually not far from the truth. So this stationary distribution does not distort too much the size of S. So the size of S is roughly proportional to this for large connected sets S. So now our task is to actually bound from below the expansion of our set. So if I fix a large connected set in my giant component in the percolated hypercube, what do I know about the number of edges going out of it? Well, we know some things. And so this work from 2024 that I mentioned before actually gives some pretty good bounds about the expansion of our sets. So for small sets S, in small connected sets in our giant component of the percolated cube, it says that the number of edges going out of S is at least linear in S. And this is not far from being optimal. So it's actually optimal up to the value of this constant epsilon 2. And when S is a bit larger, unfortunately, they cannot quite get the right expansion. So they get a bound, which is a bit worse by a factor of log d. So how to compare these two bounds and how to see that the second one is actually a bit worse? Well, think about the point where these two intervals meet. If we are at the point n to the epsilon 1, then this bound gives, this is a linear lower bound in the size of S. If you think of the second bound, then S is your n to the epsilon 1. So n is 2 to the d. So this guy, so binary logarithm of n over S, is a further d. So this and the d in the denominator, they cancel each other. And what remains is the additional logarithm of d that remains. So this additional log d in the denominator is actually the reason why the previous work does not actually get the right value of the mixing time. And the reason for this is that they actually lack sufficient understanding of the expansion of typical large connected sets. So what they can do quite well is to show optimal expansion of any set in the giant component. But connected sets are actually a bit special. So connected sets, because there are much fewer of them, they actually expand much more because of randomness. And this is the point that the previous work lacks, actually. So let me tell you maybe how one could take into consideration in an efficient way this connectivity. So let's fix a connected set, large connected set in our giant component. And let's imagine that it has small boundary. When it has small boundary, this means that if we percolate with some probability q which is close to 1, then our set S will get disconnected from the giant component with such probability, q to the power of the number of edges between S and its complement in the giant component. Okay, so let's imagine that this happened for some large connected set. What does this mean? This means that actually either our giant component before was atypically large, or our giant component after is atypically small. So you have a large piece, you take it out of your giant. So either you are very big before, or you are very small after taking out this large piece. And then here the hope for contradiction would be to try to do a fine analysis of the large deviations of this size, of the size of this giant component, which is part of what we do. So if you want to analyze this size of the giant component, and by this I denote the number of vertices inside, not the number of edges. So the upper tail here is much simpler, because if your giant is very large, so atypically large, this means that the small component outside of the giant, they cover atypically small number of vertices. And for small components, vertices in small components are easy to control via the bounded difference inequality. So changing one edge in a small component doesn't really have a huge effect. So controlling the upper tail is fine. So controlling the lower tail is actually a harder task, and this is one of our main results. So we actually managed to do this efficiently up to the value of this constant epsilon here. But there is a problem. So the result from previous paper I showed you said that so they had optimal bounds for the expansion for sets which are size n to the epsilon, and from n to the epsilon onwards, they actually had a problem. So expansion was not optimal, and if we show this, then we can show it only for 2 to the power of d divided by d to some polynomial. So this is actually much, much larger than our dream, which is some smaller polynomial in 2 to the d. So our result does not actually cover the gap that was left by previous work. And one could say, okay, maybe we can, maybe this result can be improved. So the lower bound on t is actually not this one, can be made much better, but this is unfortunately not true. And it's not true because the deviation of small components does not allow this. So our bound here cannot be smaller than something which comes from the deviation of small components. And if you compare these two expressions, you see that, well, the best thing we could have here is 2 to the d divided by d with some log correction. So there is no hope to just correct, so just fill in the gap just by looking at large deviations. But so remember, I told you that connected sets are important and not just general sets in our giant component. So for connected sets, this is actually doable. So we can reduce this bound to something which is 2 to the d to some power smaller than 1. And for such t's, the probability that we can separate a connected set from the giant component will actually be of the order that I showed you before. And this is good enough to now control the probability that such set separates. So this is the optimal deviation bound that we need. So what's the moral of the story here? The moral of the story is that if we want to estimate large deviations of L1, so of our giant component, then so these large deviations typically come from many small components which separate here and there from the giant, rather than very few atypically large connected pieces which separate from the giant. So this reason, so many small components which separate all around the cube from the giant, this is a more typical reason why your giant should deviate, essentially. So this is the rough intuition to have in mind. Let me now tell you maybe in a glimpse about some ideas which we use to prove the second result. So the fact that it's hard to separate a large connected piece from the giant. So here we start with 3 graphs. So G is our percolated hypercube. This is QDP. G1 is a sparsified version of G, and G2 is a sparsified version of G1. So you can essentially imagine that you do thinning twice, and G is your original graph. So the first thing we do is that we establish a stability principle, which says that, okay, so let's look at the step where from G1 we obtain G2. And let's look at some large connected sets in G1. So we show that the probability that some very large connected set or component in G1 actually falls apart into a lot of very small components in G2, this probability is very, very small. So smaller than the deviation bound I showed you on the previous slide. So in particular, this tells you that if you have a large connected set in G1, then when you thin G1 and when you obtain G2, then some part of this large connected set will remain connected. So some constant proportion will remain connected. And okay, so the second part is that with high probability, all vertices, or almost all vertices, sorry, in the hypercube will actually be close to large connected components in G2. So up to now, what did we do? We took some large connected set in G1, then we thinned it, we obtained G2, and we said in G2 there is some large part of the connected component in G1 which remains connected. So now this connected set, this large connected set in G2, we want to see how it will, so when we go back to G, how we will behave with respect to the giant component in G. And it turns out that if you have large connected set in G2, then with very high probability, this large connected set will become part of the giant component. And so this is the third step, because so most of the vertices actually have a lot of neighbors in large connected sets. These large connected sets will come together. And so here is somehow the contradiction. We started with G1. We imagined that from the giant component of G, we separated a large connected piece. Then we thinned a bit more. This large connected piece had a large connected subpiece. And then we went from G2 to G. And this large connected subpiece with high probability needed to be part of the giant component. So this is essentially the proof in a glimpse. So maybe this is a good time to stop and to ask if there are any questions at this point. After the break, I will continue with the diameter.
Yeah, maybe one question that I can ask, Lyuben, when you say you do for the upper tail of the size of the largest component, you say you do it with like if it was a branching process, but there's it's not really a branching process. So how do you deal exactly with those dependencies?
So
This
the
one.
upper tail here, you mean?
Yeah.
So the point is that you want to estimate the number of vertices in components of size, say at most d squared.
Okay.
This is the threshold we put on small components. And so if you add an edge to the graph, you actually do not create new small components, you can destroy some small components. But the number of vertices you lose in small components, if you add an edge, is at most 2 times your threshold.
Okay.
So now if you remove an edge, you have the opposite effect. So removing an edge could create at most 2 components which are below the threshold. So essentially the number of vertices in small components under this local changes by at most 2 times the threshold.
Okay, but then it's not really like a branching process approximation. This is rather a concentration result using these observations, no?
Yes. We don't do branching processes here.
Because
That's
I
right.
read somewhere branching process. Maybe it was before on the slide before or somewhere that I got confused.
No, so here in the upper tail, we only use the bounded difference inequality. It's not, it's nothing more complicated. It's the most standard form of it.
Okay. Yeah, thank you.
Yeah. So, if there are no other questions, maybe let me continue to the diameter. And for the diameter, let me again do a review of the literature, so what was known up to now. And as before, so GNP is the more standard model, so it makes sense to start with it. Again, we are going to concentrate on the giant component in the slightly supercritical regime, so the sparse supercritical regime. And in this case, series of authors have proved that the diameter is of order theta of log n. So concerning the hypercube QDP, bounds were established by the paper that I already told you about, by Erdekang and Krivelevich. So together with mixing time, they established a bound on the diameter, which was d cube, so polynomial one. And then the later paper from 2024 established a bound which is almost optimal, but there is this additional factor of log d squared. And again, the situation is very similar with the one for the mixing time. So one-dimensional abstractions are what decides the lower bound. So in GNP, remember, we had paths of degree 2 vertices of length log n, which end with a leaf. So this tells you that the diameter cannot be smaller than order log n. And the same thing here. So for QDP, we would expect that the diameter is again of order d, and this logarithmic correction here is actually should not be there. And this is what Bolobashko, Hayakawa, and Luchak actually conjectured, that the diameter should be just linear in d. And this is actually what happens. So the diameter is indeed linear in d with high probability. So let me just tell you some more about the approach. So in order to do this, I'll ask you to turn the hypercube in your head on its corner, so that the 0, 0, 0 corner points to the bottom and the 1, 1, 1 corner points to the top. So if you do this, you will obtain essentially a graph which has kind of levels, as in this picture. So on the bottom we have the level of 0, 0, 0, 0. This is the only vertex on this level. The topmost level contains also one vertex, and say the kth level in the middle contains exactly d through k vertices. And so for this graph, one work which was particularly useful for us was one by Anastos, Diskin, Elboim, and Krivelevich from 24, who said the following. Let's look at this graph. And they ask, okay, so what is actually the probability that we can connect the bottommost vertex to the topmost vertex using the so-called monotone path? So what is a monotone path? Well, if you think of the hypercube in this representation, it's pretty clear what it means. So it is a path which increases at every step. And so if you think about it, when you percolate with probability p equal to constant over d, then you won't be able to connect 1, 1, 1, 1 to 0, 0, 0, 0 with high probability, because so each of them could be isolated with some non-zero probability, also different from 1. So we kind of cannot expect with high probability statement there. But what we could expect is a path that goes from the first layer, so the layer of the neighbors of the 0 vertex, to the layer of the neighbors of the 1 vertex. So this we could expect that it holds with high probability. And it turns out that this event has a sharp threshold. And this sharp threshold is E. So if your constant is larger than E, then with high probability, you have a monotone path which connects the neighborhood of 0 to the neighborhood of 1. And then if your constant is smaller than E, then you do not contain such a path with high probability. So how can we use this result to say something about the diameter of graphs? Well, you can say, okay, so if my vertex 0, 0, 0 is in the giant component, then it probably expands well. So I can look at close neighborhoods. So for example, I can expose, I don't know, the 1000th neighborhood of 0. And then probably this 1000th neighborhood will contain many vertices. And then we can do the same thing with 1. So if 1 is in the giant component, then probably it expands well. So if we expand for 1,000 or 1 million layers, then we'll get probably a lot of neighbors. And then for these neighbors here, one could say, okay, but probably we can find also hypercubes, so disjoint hypercubes between these vertices, and try to connect separate vertices in these disjoint hypercubes. And this is actually the right strategy. So such hypercubes are in general not so hard to find. So our general strategy to efficiently connect vertices which are far from each other in the hypercube would be to expand a little bit from the bottom, expand a little bit from the top, find these joint hypercubes, and then try to connect them. So try to connect the vertices, the corresponding vertices, using the monotone path lemma. It's a possible strategy. It's a potential strategy to try, and it actually kind of works. So the reason why it works is the previous expansion bounds that I showed you from the 2024 paper by Diskin, Kang, and Krivelovich. They actually say the following. So sets with a large constant times d number of vertices expand very efficiently. So if I go back to the result, they actually say such sets expand by a constant factor until some very large threshold. Okay, so if they expand with a constant factor and we look at sufficiently a large neighborhood, so we iterate this observation many times, then in such sets of size large constant times d, we're going to find one vertex, at least one vertex, which expands really well. So at least one vertex which looks like the 0, 0 on the picture or the 1, 1 on the picture. And okay, if we have two vertices that are in the giant but are far from each other, then close to one of them we find a very well expanding vertex, close to the other one we find a very well expanding vertex, and we can do the strategy that we saw here. So that's very nice, and that actually works. But it actually works only for C larger than E. So it doesn't quite take us to the threshold 1, which we would like, because so C equal to 1 is the point where a giant component emerges. So we are unable to treat the entire supercritical regime with this observation. And okay, then we could say, but we can bootstrap this monotone path lemma. So even if our probability was a little bit smaller than constant, then probably we could work with it. But unfortunately, it is not. So when your constant C is smaller than E, not only the probability of such monotone path is small, it is actually exponentially small in the dimension. So it's so small that the previous bootstrapping strategy is actually useless, so we cannot use it. So the solution to this problem is to, as some of my collaborators said, to add twists and turns. So what does this mean? The monotone path that I showed you uses, so it goes strictly up every time, which means that it uses each of the dimensions exactly once. And this is a little bit, well, it restricts the flexibility of what we're doing, so to say. So the solution to this was actually to allow using every dimension a fixed number of times, so a large fixed number of times. And it turns out that if you allow some k, so to use every dimension k times for some large k, you can actually obtain a sufficiently large probability bound for the existence of such, I wouldn't say monotone path, but maybe a twisted path from 0, 0 to 1, 1. And then this is not with high probability. So we have some error bound, which is polynomial in D, but it's enough to actually do the bootstrapping strategy that I showed you 2 slides ago. So again, when we expand sufficiently, we can find much more than d to some power number of cubes, so much more than any polynomial number of cubes. And when we do this, then we are essentially done. So the bootstrapping works exactly as expected. The proof of this result is, I would say, a bit technical. I'm not going to talk about it, just say that it's some delicate second moment argument over such paths with some additional special property that makes computations easier. I'm going to finish with 3 open questions. I think the first one is one of the famous open questions of Remco. He really likes this question. So Remco asked us, can you do the barely supercritical regime? So can you say something around 1 plus little of 1? And our methods extend maybe to some decreasing epsilon, but we don't really know what happens there. So maybe if one decides to go into the critical window and slightly above the critical window, then new ideas will definitely be necessary. One very ambitious open problem will be to actually pinpoint the right constants, which I think is quite difficult, but also it would be much appreciated by by both the combinatorial and the probabilistic community. And one interesting direction would be to say, okay, so the hypercube is some high-dimensional graph. So can we do something similar to other high-dimensional graphs? So for example, in recent years, people were quite interested by this so-called permutahedron, which is obtained as a convex hull of the set of permutations in so on n elements in dimension n squared. So this has been quite studied as some nice polytope, but I don't think that people have looked at its expansion properties even without percolation. So that's also one possible direction. And upon this, I'd like to thank you for your attention and happy to answer any questions.
Thank you, Lyuben, for this nice talk. Are there questions? Yeah, I have one more question. You said that the lower bound for the mixing time is not finding bending path of order D inside the giant component. Is that true?
It is.
Or
So
will
it
you
comes
find
from this.
actually path of it is.
Yes, you're going
So
to find
it's the
bending
same.
paths.
So in particular, you can also find a lower bound on the relaxation time, and you can show that there is no cutoff for the mixing time, right?
I think so, yes.
Okay.
Yes. So we
And
didn't
the other question,
actually
so
say
this,
anything about the question of relaxation time, but I think that you're right here.
okay. And the other question, this this upper bound on the mixing of Fontolakis and overall subsets with basically minus k fraction of vertices. Is this similar to the bound that this average conductance method used by Lovaas and Kanan gives, or is this better, or does this have any prerequisite, any special
Uh,
this bound?
if let me see, is it a bound? So I think that the bound that you're referring to is essentially a continuous version of this where you integrate and this phi of k to the minus 2 is actually phi of x to the minus 2. So there is indeed some integral form of this
Yeah.
bound, which is averaging in a slightly different way, but I think that these are essentially equivalent. So these bounds you can obtain from the other
Okay.
one by
Got
cutting
it.
into pieces and then taking somehow the worst case for every piece. So these are your pieces here, the intervals between 2 to the
Yeah, the
minus
other
p
one I
minus
think
1 and
had an error term, which was an additional 1 over egg or 1 over something, right? Which does not appear here. That's but other than that, it looks similar. Yeah. Okay.
yeah. Um, yeah, I remember that we actually had the two of them, and we decided to use this one because it was somehow more convenient from computational point of view. But when we tried to do the computation, we actually saw that they're equivalent for our case.
Okay. Other questions? No, no question. The big room. Well, then if there are no more questions, then I would say let's thank Lyuben again for this talk.